So let's continue with this example of a list monad. What are the algebras for the list monad? The ones that are compatible, right? So let's start with this condition, right? So eta will create a singleton list, and it means that sigma. So we have some kind of some algebra sigma, right? And we know that when it's acting on a singleton list, it will give us the value of x, right? That's what this means. So that's a condition on sigma. This is how it should act on singletons, right? Because eta for a list is a singleton. Now sigma also has to be defined for any list, right? So of integers, let's say. Well, let's not specify what, right? So we have some type for which we are defining an algebra, and we want this algebra to make this algebra compatible with the list monad. So sigma acting on an empty list has to be defined as well, right? We'll just call it E, okay? It's some value. I don't know what it is, right? Now, what I'm going to say is that algebras that are compatible with the list monad have to be monoids. Okay? So sigma acting on an empty list gives us some value E. And I'm claiming that this is the monoidal unit. Okay? You don't believe me yet, probably, and shouldn't, right? How do I define multiplication? Well, I'll define a multiplication acting on, acting on, let's say I want to multiply x times y, right? So this is like monoidal multiplication, right? I will define this by definition. This is equal sigma on a list of x and y. Right? Now let's see. Let's check the unit law, right? So a unit law would say that E, let's say left unit law. E times x must be equal to x, right? So what's E times x? Well, it's sigma, and what is E? E is an empty list, right? Sigma on an empty list, right? X is a singleton list, right? Now, I'm going to use this coherence condition, which says that I can first flatten the list, right? And then evaluate. So if I flatten it first, you know, this is an empty list, this is a singleton, I'll get a singleton list, right? So it will give me sigma of x. Which is my x, right? So I get the left unit law from the coherence condition. And moreover, you know, from the same coherence condition, I will get also associativity law, because as you can see, you know, it's like I can always interchange evaluation with flattening, with concatenation of lists, right? And list concatenation is associative. So I can create compositions of, you know, multiplication of multiple things, and then I can say, well, it really doesn't matter in which order I'll evaluate them, because I can always flatten first, concatenate first, and the concatenation always gives the same thing. So it turns out that the monad algebras for the list monad give you monoids. Okay, so it's a very strong condition. An algebra is compatible with a list monad is a monoid. So the category of, well, I didn't say that yet, but obviously, no, it's not so obvious, but algebras that are compatible with a particular monad form a subcategory of algebras for this endofunctor, right? I mean, I would have to show you that, you know, the morphisms between these algebras that are compatible with the monad also compose to something that's compatible with the monad, right? But that's kind of automatic, and it's very easy to homework, right? So the category of monad algebras for the list monad is equivalent to the category of monoids. Remember that. It will come up later when we talk about Lapierre's theory. Okay? So this is the intuition. There's a little bit of hand waving, right? But you can like go through this at home and figure out all the details. So now let's go back to the original question. This was sort of a digression because I wanted to show you this theorem that says that well, first of all, we know that for every adjunction, we have a monad, right? If you have two functors, f left and right, if you combine them in a particular order, they give you an endofunctor, and this endofunctor is a monad. If you combine them in the opposite order, you get a comonad. So every adjunction generates a monad and a comonad. The question is the converse true? It's like if you start with a monad, can you find an adjunction for this monad that generates this monad? And as I said before, yes, the answer is yes, and there are actually many such adjunctions. And now I want to show you one of these adjunctions. Okay? So in order to generate this adjunction, starting with a monad, when I start with a monad, I have just one category, C. For adjunction, I need two categories and two functors. So I have to generate this new category, okay? And it turns out that one of the possibilities for this adjunction that will generate the monad is the Eilenberg Moore category, which is the category of algebras for this monad. Okay, so which are the algebras that are compatible with this particular monad. Okay, so this will be my left category. So my left category, my right category is some C in which I have these monads, right? I have this monad T acting on category C. My left category will be the category of monad algebras for T, which is also called C with a superscript T. Okay? That's the Eilenberg Moore category. There is also C subscript T, which is the other one that generates the monad through adjunction, which is the Kleisli category. So if you see these things, this is mathematical notation for these things. This is Eilenberg Moore, this is Kleisli. But I'll talk about Eilenberg Moore, okay? So this is a category which has as object these things, right? The algebras with these coherence conditions. So every algebra in that category satisfies these coherence conditions for this particular monad. Okay? And of course we have morphisms in this category CT, which are morphisms between algebras, right, that satisfy this condition. So we have to keep all of this stuff in mind. Now we have to come up with these two functors. Okay, one functor. So this is the category CT of algebras. Right? One functor is easy. Well, we'll call it a forgetful functor because it forgets that it's an algebra. Okay, so you start with an algebra. You have some algebra A, comma sigma, and it maps this to A. Just forgets about sigma, okay? It is a functor, okay? If you, how does it work on morphisms? Well, if you have a morphism between two algebras, you know, A sigma, B lambda, right? It's a morphism from A to B to begin with, which satisfies this additional condition. But we can forget about this condition. It's just a morphism, right? So U on this F just gives you F, okay? And of course you should check also that when it acts on an identity algebra, it will create an identity morphism, but that's sort of follows automatically. These are simple things to check. So the real problem is finding this functor that goes from C to CT. Okay, so this a joint functor to a forgetful functor is usually called a free functor. So this is forgetful, free. Okay. But the question is, given an object A in here, how do I generate an algebra? I have to generate an algebra, right? And it has to be an algebra that's compatible with my monad, right? It has to satisfy these conditions. Well, so let's look at the definition of the monad, right? Look at this guy. We have something that looks like an algebra, right? I mean, if I rename this thing to some B, say, then I have TB going to B. That looks like an algebra, right? Now, this is a natural transformation. So actually, this is like a very good algebra because it gives me an algebra for every A. It gives me an algebra. So it's like a sort of polymorphic way of generating this huge category of algebras. So I'm going to define this functor F. When it's acting on an object A, it gives me an algebra whose carrier is this B, which is TA, and whose evaluator is mu A. right? Because, well, what's an algebra for that has a carrier TA? Well, it has to go from TA to TA, right? And this is exactly what mu A does. Voila. Right? So for every object A, it gives me an algebra. Now, is this algebra compatible with my monad? That's a good question, right? Because if I want this to go into the Eilenberg Moore category, it has to generate algebras that are compatible with this monad, right? So, so the first condition is, well, what's my sigma? My sigma is mu, right? So this condition just says that mu after eta is identity. Okay? Well, that's a monad law. That's the right unit law for the monad. That's this law that we drew like this. This is eta, this is mu, this is t, this is t. Okay? So if you remember this, if you don't remember what a monad law is, well, remember this picture, right? That you can pull these things and it's equal to identity. Okay? So this one works, okay? What about the second law? Okay, the second law, this is a little bit more complicated, right? But sigma now is again mu, so it is essentially mu after mu equals mu after t mu. Okay, that's the second law of the monad. Okay, and maybe just to show you, okay, that this is really what it is. Because we've seen the monad laws in pictorial form, right? We've seen this. Mu is equal to, it's essentially associativity law for mu. That's the second monad law, right? That you can switch them, associated differently, right? Now, this is why we needed this, okay? Because it tells you that horizontal composition of T after mu, okay, composed with mu equals mu composed with T in this order, vertically composed with mu, right? You remember this? This is horizontal composition along this line. Then you follow it with vertical composition, right? And here is the other one. Which one is this? This one, yeah. Because this is mu and this is t. Okay? So that's the monad law, right? Now if you look at this, okay, mu times t, if you look at the component of this, okay, so this is just mu at TA, right? And it's combined with mu a. And this is, or this this is the right composition, right? So this is whiskering on the left. So that will give me T acting on alpha, which in this case is T acting on mu A, right? Composed with mu A. Here the composition is the composition of morphisms, because this is a vertical composition, so we are just composing morphisms. This is just, mu A is a regular morphism, no longer a natural transformation. I've taken a component of A, right? So if you look at this as a diagram, you know, you have T and you have mu going this way. Mu goes from T square to T, right? And then you compose this with another mu. It's all the same category because it's an end factor, right? So this is this equation, if you draw it as a diagram. So this is my vertical composition of this with this. This is my horizontal composition, the whiskering, right? It just shows you that if you pick an element A here, an object A, that this is what happens. This is mu at A goes from here to here. I mean, this is something that's it's a nice exercise to like go through this, because this is juggling very different pictures, right? But this is right. So this is this equation. Okay. So what did I show you? What I wanted to show is that coherence conditions for this algebra to be compatible with T as a monad are satisfied because of monad laws. Okay? So just because of monad laws, this created a monad algebra. So this is actually a monad algebra. So F creates a monad algebra. From any object A, it creates a monad algebra. Okay? So now we have two functors, left and right. The right functor is this forgetful functor. The left functor is this free functor that generates these algebras. And I will call this functor ft, and the other one I will call, well, this is a different thing, right? Because it depends on the monad t, and the other functor is ut. Okay, so but I haven't shown you. Now, if I want to call this a free functor, I will have to show you that this is actually an adjunction, right? So let's see. If this is supposed to be an adjunction, okay, then an adjunction is defined by unit and co-unit. Okay, so what would the unit be? And we are reusing the same Greek letters all over because they are actually the same. Okay, it's like, by the miracle of all these theorems, it actually gives you the same. So the unit of an adjunction is supposed to be something that goes from the identity functor to the functor u after f. Okay? If you remember, so in our case, utft, right? So u is right after left, and the co-unit was going the opposite direction, but also with inversion. So ft after ut going to identity. Okay, so let's see, what is this? So if we take a component of this, this is a natural transformation. We have to define it, right? If we want to show that this is an adjunction, we have to define it. So let's define a component of it. So at some object A, ID on A will give us A. Okay, so that's simple. On the right-hand side, what do we want? Well, acting on some object A, the free functor was supposed to give us TA nu A. Okay, that's how I defined F. Okay, now I want to act on this with the forgetful functor, which means I'm forgetting this. Okay, so what is eta? Eta is supposed to go from A to TA. Do I have something that would give this to me? Well, I can use my monadic unit, right? This guy goes from A to TA. Okay, so I have a candidate for unit. For the unit of adjunction to be the unit of the monad. Has the same signature, right? What about epsilon? Okay, epsilon is a little bit difficult because epsilon acts on an algebra. So I have to start with some algebra, let's say A sigma, right? So the right-hand side will just give me A sigma again. So acting on algebra A sigma, it gives me A sigma. Not a big deal. This one will forget about sigma and will give me A. And the free functor will give me TA comma nu A. Okay? So the result of the left-hand side acting on A is this algebra, TA nu A. And I have to map it to ID acting on A, or on A sigma, which is A sigma. Okay, do we have a candidate for this? Well, it has to be an algebra morphism, right? So it has to map carriers. So it has to map TA to A. Okay, where do I have something that maps TA to A? Can anybody see it?
Yeah, sigma.
Sigma, right? Well, I could write sigma goes from TA to A. Okay, so I can use sigma as my epsilon. Okay? And now, of course, I have to, in order to prove that this is actually an adjunction, I would have to prove the snake identities for unit and co-unit, okay? Or otherwise known as triangle identities. And this is, I will leave this as a homework, okay? You have all the tools to actually do this. You know how to compose natural transformations.